evaluating large language models' ability to answer zero-shot natural language queries.
In today's presentation, we're going to go over the big picture, the background, the goals for this project, how we went through like our methods to get to achieve our goal, our results, and our conclusion.
So our big picture. So our research is based around hopefully combating the problems that data scientists face in their work. So if you're unfamiliar with what data scientists do, essentially they use NumPy and pandas to extract meaningful data from data sets, and then they can use that data to make predictions. They can do this in all types of different fields, ranging from medicine all the way to like business and economics. So it's extremely important work. An example of a data science task would be like finding the mean of a column in a data set, or finding the correlation between two columns in a data set, something like that. However, one of the main problems with data science is the speed in which tasks are executed. Because it's a lot of NumPy and Panda plug and chug, it can take a while for like simple tasks to like be executed. And this can, especially with how fast the industry is moving nowadays, it just leads to data science being like kind of left in the dust compared to other work, right? And so hopefully by automating data science, we can make it more applicable to other types of research. So for this, we looked at natural language processing technology, which is an extremely fastly moving technology in the world of AI. I'm sure you've probably heard of it or used it. It's responsible for the likes of ChatGPT and other AI models. And so we were wondering if we can use large language models, which is a specific like subcategory of natural language processing, to help automate data science tasks. And so to evaluate whether or not large language models, or LLMs, are equipped at performing these types of tasks, we needed to create a sort of data set benchmark, or a sort of basis to judge the model on. And so for this, we created a bunch of data sets. And then based on how the model performed on that, we could like judge whether or not this type of model is good just as a baseline. And then we could potentially improve it with different types of GPTs and different types of models. Next slide.
Yeah, so there definitely does exist previous work done for a similar concept. Of such, one popular concept is AutoML, which also focuses on automating data science tasks, just not via pure natural language like our project. It has gained popularity in automating tedious tasks like data preprocessing, and you can see the workflow diagram on the right. Next slide. Yeah, so as such, we have already seen that LLMs can be a very powerful tool for understanding natural language as well as generating text and code. Using this fact, we have incorporated prompt engineering techniques like chain of thought and reflection, which are essentially ways to quote-unquote improve our prompts for our LLM to yield high-quality zero-shot queries, which are essentially queries or prompts that they have not been explicitly trained on. We have also noticed that this is a novel attempt, there's not much of a standardized benchmark or evaluation metric for the LLM, as Charles previously mentioned. Hence, we have also manually created them on our own, which we'll explain later in the methods section. Next slide.
All right, yeah, so we had a couple of goals going into our research. So number one, we wanted to basically take an LLM and see if it could operate as a data scientist. So our LLM is composed of a GPT 3.5 action plan generator and an executor that's just capable of answering natural language questions that would typically be asked in data science. You can almost think of the LLM as like an agent in a code-based environment using NumPy and pandas to answer questions. And so basically, it takes in an input and then uses a like code-based answer as an output. Our second goal was to create a benchmark, just a bunch of toy or mini data sets with their corresponding questions that we could use. Typically, the questions will be asked in typical data science, as typical data science questions, and then you could see how the LLM performs with those questions. And then from there, kind of just using that baseline, we could see whether or not LLMs are kind of equipped at answering these types of tasks, and then we could potentially improve the model with different types of GPTs. Next slide.
All right, so one important step was to create the benchmark for our model. And for that purpose, we used GPT 3.5 to generate 50 toy datasets. An example prompt we gave to GPT was generate a dataset with 100 rows and 6 columns about the weather in different cities. That toy dataset is displayed on the screen right now. All datasets ranged from 50 to 300 rows. Small datasets contain less than 100 rows, medium datasets between 100 and 200, and large datasets have over 200 rows. Each dataset also comes with 20 questions that ask about some information in that particular dataset. The questions were designed with varying difficulty levels. Some were pretty straightforward, like how many rows are in the dataset, while others were slightly more challenging, such as what's the correlation coefficient between the temperature column and the humidity column. The answers to those questions were found manually using pandas and NumPy and were then compared to the answers generated by the model. Next slide, please.
Yeah, so as Abdu mentioned, each of the queries from the benchmarking datasets gets passed through a mechanism that we call the action plan generator. So broadly, the action plan generator takes a query from the benchmarking dataset and then converts it into a series of smaller steps that build on top of each other, eventually reaching to the final answer. In order to generate this action plan, we feed the GPT 3.5 agent some background information about the dataset so that it is able to write the appropriate steps to solve the query. This whole process is based on the novel technique named chain of thought prompting and is shown to drastically improve the results in LLM responses. So after these queries are broken into smaller steps, GPT 3.5 writes NumPy and Panda code to answer the smaller steps, and an example of this is on the right side. In the diagram, this is an example of an action plan list and it is parsed through, and the code is generated for each of the individual parts, eventually reaching to the final answer. This segmented approach significantly increased our accuracies and also accounts for errors in query language.
Yeah, so here you can just see an example of how the action plan generator works with the rest of our model. So we see that we start off with a toy data set that we input ourselves, so that's zero shot prompted, along with the original query that we want to have. And then we parse that through the action plan generator, which iteratively generates as a GPT model. It generates a list of concrete actions that it then writes NumPy and Pandas code for. Along with the original data set, that code is executed in the LDS, which ultimately produces a final output. And on the next slide, we can see an example of that. Yeah, so here is an actual example of our model working on a small data set called zoos, along with the query, what is the 26th percentile of the date founded column? So like I said, the data set and the query are inputted into the GPT-based action plan generator, which then creates a natural language plan and then iteratively writes Python code, Pandas code, and NumPy code for that. That's then run through the LDS, and then we have our final output of 1934. Next slide, please.
These are the results that we have obtained from implementing the methodology explained. For small data sets, we got 302 out of 340 correct answers, giving us an accuracy of 88.824%. For medium-sized data sets, we got 280 out of 320 correct answers, giving us an accuracy of 87.5%. And for large data sets, we got 304 out of 340 correct answers, giving us an accuracy of 89.412% and an overall accuracy of 88.6%. Now, the main errors that were noticed during this results were the logical errors in which GPT was not able to comprehend the question properly, and in cases where two outputs were needed. For example, when mean and median were asked, only one output was given. And also there were formatting errors in case of outputting decimals and percentages. Next slide, please. Now, the key takeaways that we have from this project are GPT-dependent models are capable of quickly automating low-level data analysis, and that GPT 3.5 is a viable model to generate pandas and NumPy code to execute data tasks. Applying chain of thought prompting and Seika and language conventions drastically improves accuracy. In the future, we plan for more LDS refinement and incorporate techniques like reflection, use larger toy datasets and increase testing, and explore changing action plan mid-execution in case we get a wrong answer, using GPT-4 instead of GPT 3.5, and evaluate the model's ability to generate data visualizations. Next slide, please.
All right, so this project would not have been possible without the help of some important contributors. And for that reason, we would like to thank all the mentors and researchers that helped us throughout our research. Next slide, please. And before moving on to our Q&A session, these are references.